Hasn't science disproved Christianity? No, it hasn't. Any questions? Okay, maybe I better provide a little bit more detail. So here we go. I think when people ask this question, they probably are thinking of usually the following things: the age of the earth, evolution, and the Big Bang. In fact, last night at the session, I asked people what they thought other people would be thinking, and they basically came up with these three things. So these are the three things I'm going to talk about. And in particular, with respect to the age of the earth, I'm going to talk about radiometric dating in the geological column. With respect to evolution, I'm going to talk about the origin of life and the impact of mutations in natural selection. And with respect to the Big Bang, I'm going to talk about the origin of the universe and the distant starlight problem. Now, I think it's fair, I'm going to have to issue a warning here. This presentation contains a lot of slides that contain a lot of information. Viewer attention is advised. Not only that, I put this talk together from 4 separate talks that each take an hour. So I hope you had lots of snacks. And it may seem a little bit like this from time to time. All right, to answer this question, whatever it deals with, you need to be equipped with information. And actually, that's what Creation Ministry is all about. It's providing you access to information or getting information into your hands so that you can be equipped to answer these kinds of questions, particularly from the scientific perspective. And we have a number of mechanisms for doing that. One of those is a website. Gives you access to over 11,000 articles that have been written on this topic, covering all the different scientific disciplines. There's a new article featured on the website 6 days a week, and it looks like this. That's the featured article for that particular day, and you can see it actually covers stuff kind of a little bit outside the scientific realm as well. Now, if you make this website the homepage on your web browser, whenever you launch your web browser, you'll be able to go see what today's article is. Of course, to do that, you need to know the web address, right? Now, it's pretty complicated. I don't know why they picked such a complicated web address, so you'll need to pay really close attention to the screen for this. You got that? All right. I'm sure Brian knows what it is anyway, if you don't need to go. Now, if you click on the title there of the featured article of the day, you'll go to a page that looks like this, and you can read that article. And that article will likely have a lot of links in it to other articles on the same subject, so you can read as long as you've got time to do so. The other thing you'll notice here are events, a list of events situated near to where you are. Who knew, right? Big Brother is watching. They know where you are when you log on to the internet. And that's because another mechanism that CMI has for getting information to people is speaking at events like this. In fact, many of our speakers are out every weekend, pretty much, speaking in churches. And those of you who are here from different churches, if you would like to have a CMI speaker come to your church, wait until this picture shows up on the front page, click on that title at the bottom, and it'll walk you through the process for doing that. Now, another way we have of getting information to you is a store. There's a little tab at the top that says Store, and if you click on that, you'll get a page that looks like this. And you can see down the left-hand side, it has everything categorized. And if you click on one of those categories, you'll get a list of all of the resources that are available for that particular category. And you can get a little burble there, you can read about them, and you can order them through the store, and they'll be sent to you. Yet another mechanism we have is a free email newsletter called InfoBytes. Looks like this. It highlights a number of articles that have appeared on the website in the last little while, gives you a couple of sentences to tell you what it's about, and then a link. So you can click on the link and go directly and read the article. And if you'd like to start receiving this newsletter, we're going to circulate some clipboards now. Hello, clipboard people. That has a form on it that looks like this. And if you would like to fill in your name, if you'd like to receive this, if you fill in your name and your email address and your postal code, and then keep it moving around so everybody gets an opportunity. I'll collect these at the end and we'll send them into the office, and you'll soon start receiving these. Okay, now let's get on with the main event. But before we hop into a bunch of details, there's some things we need to mutually understand about science. You know, a lot of times you can get into disagreements. Basically, if somebody put it the other day, you have the same vocabulary, but you're using different dictionaries to define the word. So it's very important we understand what we mean by science. So we're going to go through some things about science. Well, what is science anyway? Well, there are lots of definitions used from time to time. Things like, well, science is what scientists do. Well, what do scientists do? Well, science, silly. Okay, so that's kind of a circular argument. But here's one I got from Wikipedia. Now, I understand Wikipedia, you need to be careful with the information from Wikipedia, but this is a pretty good definition of science. It's an enterprise that builds and organizes knowledge in the form of testable explanations and predictions about the universe. And as you see as we go through this further, that's very important. Another thing to recognize is that not everything that presents itself as science is the same. It's not the same quality. That's illustrated by this quote from Science magazine, one of the two probably most prodigious scientific publications in the world. This gentleman says, the goal of physics is to understand the basic dynamics of the universe. Cosmology is a little different. The goal is to reconstruct the history of the universe. So we've got sciences like physics, where the goal is to understand the dynamics of the universe, that is, how the universe operates. We might call that operational science. Then we have sciences like cosmology, where the goal is to reconstruct the history of the universe, and we might call that historical science. Now, science actually is all about doing repeatable experiments, right? Scientific method is based around doing experiments that anybody can do anywhere, anytime, as long as they follow the procedure. That's emphasized by this quote, again from the same article in Science magazine, but a different person. He says, a basic tenet of science is that you can do repeatable experiments. Now, that's actually part of a larger quote in this same article, where he says, cosmology may look like a science, but it's not a science. The basic tenet of science is that you can do repeatable experiments, and you can't do that in cosmology. Okay, so let's go back to this slide again. You can say that operational science, like physics, is something in which you can do repeatable experiments. Historical science, like cosmology, you can't do that. And so that raises the question, I think, legitimately, is whether or not it's really legitimate to call this stuff a science. Now, if we put these two quotes together, we get something that looks like this, right? The goal of physics, et cetera, et cetera. Now, with a little bit of word substitution, we can transform this from the physics domain into the biology domain, in which case it would look like this. The goal of biology is to understand the basic dynamics of living things. Evolution is a little different. The goal is to reconstruct the history of life on Earth. Evolution may look like a science, but it isn't a science. A basic tenet of science is that you can do repeatable experiments, and you can't do that in evolution. Well, isn't that interesting? Now we can change the labels on this diagram, and it looks like this, and it's all still perfectly applicable. Now, the next point is maybe a little bit counterintuitive. Science doesn't prove anything to be true. It only proves things to be false. This is illustrated by this exchange between a letter writer and the letters to the editor of, yet again, Science magazine, where the letter writer said, the title of the 6th May News of the Week story, at long last, Gravity Probe 8B, satellite, proves Einstein right, made me cringe. I find myself frequently repeating to students and the public that science doesn't prove theories. Scientific measurements can only disprove theories or be consistent with them. Any theory that is consistent with measurements could be disproved by a future measurement. I wouldn't have expected Science magazine, of all places, to say a theory was proved, and the editors agreed. They said Bennett, the letter writer, is completely correct. It's an important conceptual point, but we blew it. To give you a sort of a more practical example of why this is so, consider the following. Here's the theory. If I eat a large pizza, then my stomach will be full. Well, observation is my stomach is full. So the conclusion then must be that I ate a large pizza. But I could have eaten a very large steak as well, right? So the observation of the expected result doesn't actually prove the original premise. Looks like this in a diagrammatic form. Here are all of the possible ways that my stomach could be filled, and here is the one that occurs if I eat a large pizza. Now, another a corollary of this is that it's since observations don't prove theories, the observations that are consistent with theories don't prove theories to be true. It's really the observations that aren't consistent that are the significant information. So let's suppose this is a set of the observables or data that we have, and we have two theories. The first theory explains these, and the second theory explains these. Now you can see there's a very large segment that they both explain, right? So based on those observations alone, you cannot actually distinguish between those two theories. And a particular application of this to evolution, which we'll be talking about later, are the observations about mutations, natural selection, and speciation. The observation of these things does not prove evolution to be true, like many people say, because those same three things are consistent with the creation account. Then there's this issue. If you have a theory that explains all of the observations, and then there's a new observation that it doesn't explain, that's inconsistent with the theory, that's a clear indication that the theory, at least as currently expressed, is wrong. Similarly, if you have something that the theory requires in order to be able to be true, and it is not possible, maybe it contravenes the laws of physics, then that's also a clear indication that the theory is not correct. And that brings us to this idea of falsifiability, which was first put forward by a philosopher of science called Karl Popper. He said, in effect, that a proper scientific theory should make predictions that can be falsified by testing using repeated experiments. Because if you can't falsify a theory, then it's not really very scientific, because science can only falsify theories. And if it can't be falsified, Now, another thing that maybe is counter to what we normally hear is that data don't speak for themselves, right? This was actually a quote I got from the National Post from an economist who mess around with data quite a bit. And he said, data cannot speak for themselves. They have to be interpreted through a theoretical model. Extracting inferences about causality requires an understanding of theory, statistics, and how the data were collected. Okay, so they need to be interpreted through some sort of model. That then brings us to this idea of a ruling paradigm, which was introduced by another philosopher of physics, Thomas Kuhn. This ruling paradigm is something under which science is normally done that is just assumed to be right. And data are always interpreted within this paradigm without questioning it. Data that turn out to be inconsistent with the theory are either treated as errors by the researcher, he just made a mistake, we can ignore that, or they're dismissed because the researcher is judged not to have the appropriate credentials. That guy, he's a creationist, what does he know? Or they're dismissed because the researcher is considered to have unacceptable political leanings or funding sources. Or, if they can't do any of those things, then they will accommodate these inconsistencies within the ruling paradigm by tacking on a bunch of ancillary hypotheses, kind of like Band-Aids, right? But eventually, these will become so numerous that the whole thing just collapses under its own weight and gets replaced with something else. Probably the archetypical example of that is the geocentric model of the solar system. The scientists back there, when they found that they couldn't explain all of that the motion of all of the planets was anomalous, they kept adding things here and there in a very ad hoc manner, until finally it just got too cumbersome, and somebody else, a guy called Galileo, came along with a much simpler idea. All right, so then if we go back to this picture again, we find out that in both sciences, it calls for a lot of interpretation of the data, and that's done under some theory or ruling paradigm. But when you make that interpretation, you need to do a lot of speculation. And the speculation will depend on the presuppositions that underlie that ruling paradigm. So now I'd like to talk about the presuppositions that underline what I would refer to as mainstream science. Fundamentally, there's this issue of naturalism. That is, that nature is all that there is. sometimes referred to as materialism. That is, that matter is, and its interaction with itself is all that there is. And that's a fundamental presupposition in mainstream science. But it actually is a secondary presupposition that is underpinned by the idea that man gets to define what's true. And man has simply defined naturalism to be true. Another assumption is that the laws of physics apply universally, that is, for all time and all space, except, as we'll see a little bit later on, when they don't. And then that's miracles. The ruling paradigms that have come out of this are the Big Bang for interpreting cosmological data, the nebular hypothesis, which is the story about how stars and planets form, uniformitarian geology, which I'm going to talk more about, abiogenesis, or the origin of life by naturalistic means, and evolution. Now, if we switch over to someone who is doing science from a biblical perspective, they'll have a different set of presuppositions. They'll start with the presupposition that it's God that defines what truth is. That, of course, means that the Word of God, the Bible, is true. Now, because God is a God of constancy, not chaos, we would also assume that the laws of physics apply universally, except when they are augmented by God's direct action. This is not a case of, well, I don't understand how that works, so that must be just the way that God did it. That's the sort of God of the gaps approach. I have a gap in my knowledge here. I don't understand it. I'll just say that's the way God did it. But what it means is that when there are miracles described in the Bible, that's a clear indication of God's intervention. Now, out of this ruling paradigm, we read the Bible, it's true, we take it as read. The ruling paradigms for interpreting scientific data are that creation happened in 6 days, 6 24-hour days, that, whoops, back up, no. Sorry. 6 24-hour days, that life was created, each after its own kind, and all that happened about 6,000 years ago. That initial creation was perfect, subsequently spoiled by sin, that there was a global flood about 4,500 years ago, and humans all descended from 2 people and spread around the world post-Babel. Now, all of these things, none of these things are particularly scientific. They're just a record of the historical account in Genesis, but they all impinge on various aspects of science. And so we expect to see in science outcomes that are a consequence of these things. And these presuppositions have a very significant impact on those outcomes. For example, consider naturalism, materialism, the impact of that on the outcome of trying to define or describe or theorize about the origin of the 747. Right? The evidence we have is the 747. We can see it, we can touch it, we can feel it, we can examine it, we can look inside it. We know a little bit about how it works. If you look at all of that evidence and try and create a story about the history associated with that, about how it came into existence, and you don't impose any external constraints on the answer you're allowed to have, it's pretty obvious it happened by design. However, if you say you have to explain its origin using only natural processes, or using only whatever matter exists and how it interacts with itself, then you're forced to conclude it happened by accident. You know, maybe something like a tornado going through a junkyard and leaving the 747 there. Now, that doesn't make that answer right? Because we know it's not. But it's the only option you have because of your presupposition. Similarly, if we do the same sort of exercise with the origin and diversity of life, if we look at the evidence and try and construct a story, a history, about how it came into existence, and we don't constrain the answer we're allowed to have, pretty obvious it happened by design. You saw a quote earlier from Richard Dawkins. Another quote was, "Biology is the study of complicated things that look like they were designed for a purpose." Maybe that's because they were. But he doesn't accept that. He says we have to explain it by natural processes. Ergo, he has to come up with some story that it happened by accident, like evolution. The significance of all of this is really well captured by this quote from an article by this guy that he wrote in the New York Review. We take the side of science, and by that he actually means materialism, as you'll see in a minute, in spite of the patent absurdity of some of its constructs, in spite of the tolerance of the scientific community for unsubstantiated just-so stories, because we have a prior commitment, a commitment to materialism. It's not that the methods and institutions of science somehow compel us to accept a material explanation of the phenomenal world, but on the contrary, that we are forced by our a priori adherence to material causes to create an apparatus of investigation and a set of concepts that produce material explanations, no matter how counterintuitive, no matter how mystifying to the uninitiated. And then he writes, moreover, that materialism is absolute, for we cannot let a divine foot in the door. What an honest man. To paraphrase him, scientists have built themselves a box called naturalism. It's not required by science, but they've built it anyway. And they're not allowed to think outside the box. And it doesn't matter how silly their explanations are, as long as they all fit inside in the box, all the other scientists will call them credible. And the whole reason for doing that, it's got nothing to do with science. It's to not let a divine foot in the door. Okay, with that in mind, now we'll get to the meat of the stuff. But this is all really kind of good stuff, because often when people get arguing about the details of this or that, and you say, hang on a minute, you understand that, boo, 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 and you go back up to the more general stuff, and then there's less argument about the details. All right, let's talk about the age of the earth. Oh, man, I'm way behind. All right, how do you know how old something is? Well, how old do you know? How do you? You have a birth certificate, right? Which is a written record attesting to its history. The most reliable way to know how old something is just to have this written record, provided by a reliable witness and recorded by a reliable scribe on behalf of that witness. In case of the birth certificate, that's the Registrar General. And that's exactly what Genesis is regarding the origin of the universe and all that. The witness is God, and the scribe is Moses. Now you'll notice, this is my birth certificate. I was born on the 6th of March, but the birth wasn't registered until the 17th. I guess they were trying to decide whether to keep me. And I didn't actually get the written record until several years later. So it's not necessary that all of this happened contemporaneously. Now, if you read through the Bible, you can construct something like this. And if you work through all of this, you can figure out that according to the Bible, the earth is about 6,000 years old. That's not what you get if you Google age of the earth on Google. It comes back with this. And if you click on the first thing underneath that, you get into Wikipedia again, where it says the age of the earth is, notice a very definitive statement. There's no question about this as far as they're concerned. 4.54 plus or minus 0.05 billion years. That's about plus or minus 1%. That makes it sound like they know this age really accurately. But that isn't accuracy at all. That's only repeatability. To understand the difference, here are two targets, right? Which one of these shooters is more consistent, more repeatable, and which one is more accurate? This guy's got the closest grouping. He's the most consistent, the most repeatable, but he's way off the bullseye. He's the least accurate. This other shooter, all over the place, sort of, comparatively, but he's more accurate. So accuracy and repeatability are two totally different things. Not only that, here are two patterns again. Which shooter is more accurate? Well, the fact is you can't tell because you don't know where the bullseye is. You can't tell how accurate something is unless you know what the right answer is. All right, back here, then they say this age is based on evidence from radiometric dating. So we're going to have to talk a bit about radiometric dating. Radiometric dating depends on a radioactive decay process. A radioactive element decays to a stable element. The radioactive element is called a parent, and the stable element is called a daughter. Now, I have two daughters, and I love them dearly. So I understand this radioactive parent thing really well. Stable daughter thing? Sorry, girls. Couldn't resist. This happens with a characteristic time frame called a half-life, which is the length of time for half the amount of the parent present to change to the daughter. So, we start off at time 0 with 16 elements of parent and no daughter. After one half-life, half of the parent changes to daughter. After another half-life, half of what's left changes, and after another half-life, it looks like this. So, if you take those measurements along the bottom and do the ratio of daughter to parent, you get a number that looks like this. So after 3 half-lives, for example, the number is 7. You can put that on a graph. Number 7 corresponds to 3 half-lives. Now, there are assumptions here that you may have spotted. One is that there's no daughter present at time 0. And another one that is a little bit more subtle is that the rock is a closed system. That is, neither of these elements have been added to or subtracted from the rock since it was formed. Third is that the half-life is constant. These are all assumptions about the past that cannot be independently verified. So, how do you tell whether or not this actually works? Well, with any measurement device, what you should do is calibrate it. Calibration is the comparison of measured values coming from the instrument with calibration standards of known accuracy. And these standards are normally traceable to national standards held by some institute. Now, I think it's fairly obvious there are no calibration standards of known accuracy traceable to national standards held by a national institute for things that are millions and billions of years old. How would we know that? Well, okay, so we can't calibrate this technique, but one thing we might do is if we actually know how old a rock is because we saw it form, we might try and measure the age of that rock using one of these techniques. These are the radiometric decay chains that are typically used, and this one in particular is applicable to that scenario I just described because it's commonly used for volcanic rocks. And it's assumed, because the volcanic rock is molten before it solidifies, that any of that argon that's there, that's already there, because it's a noble gas, it will be boiled out of the rock, so that anything you see in the rock is a result of radioactive decay from when the rock got hard. So this was tried on some rocks from this unpronounceable volcano in New Zealand, which was known to erupt at 3 different times. So they got samples from these eruptions, sent them away to an independent laboratory to have their ages measured, and these are the results they got back in millions of years, right? So looks better on a diagram. And the right answer is way down here, obviously, essentially 0. So this doesn't look too good. What's going on? Well, with this particular approach, this particular methodology, the potassium-argon one, it's attributed to the presence of argon-40 in the rock when it got solidified. So at time 0, you have some argon contamination, and it just stays there. So that means, across the bottom, the ratios all change, or the measurements all change, and that in turn means that the ratios all change. So now, after 3 half-lives, instead of 7, you get 11. But if you go back to this graph and put 11 on it, you get a different age. So that assumption being wrong means you get the wrong age. And since you can never know if that assumption is right, it seems kind of unreasonable to ever assume that it is. So we can assume that, we can't assume that that assumption is correct. So that means we can't really assume that any of the ages we get from this technique is right. Okay, well, scientists aren't really dumb. So they recognized this, and they set about trying to find a technique where you might not have to make this assumption, and they came up with something that's called isochrone dating. So we have this normal radioactive decay process, and I'm now going to change the name of the stable daughter to the radiogenic daughter. This isochrone dating technique depends on the existence of a other isotope of the same element as the daughter, which I'm going to call the non-radiogenic sister. Then what they do is they take a whole bunch of multiple samples of the same rock, which might have formed with different initial mixtures of the various elements. However, they make the assumption that the ratio of sister to daughter is the same for all of the different samples at the time the rock was formed. Then what they measure is the ratio of the daughter to sister and parent to sister, and they plot that on a graph. So now we've changed this assumption for this assumption, okay, that ratio is the same in the rocks. The other 2 assumptions stay the same. Then what they do is they plot this sample or these measurements on a graph, and they get a straight line. If it all works, they get a straight line, and you can use the slope to determine the age. Now, it turns out all of these other decay chains are useful for isochrone dating, right? And in fact, in the lead case, instead of using the two transformations, they actually measure these ratios and plot them, and it's called the lead-lead isochrone technique. And here's some examples, right? Looks pretty good. Got some nice straight lines. You can see they got measurements. And the uncertainties in the measurements are all pretty small, so it seems to be working pretty well. The uncertainties, incidentally, are indicative of how good a fit to the straight line you get. So how did these work on the rocks from the New Zealand volcano? Well, not so well. Worse than the potassium-40 rock. That's the samarium, or potassium-40 technique. That's the samarium and rubidium ones, and here's the lead-lead one. Now, somebody might point out, yes, but in this case, we're not measuring the age since the lava hardened. We're actually measuring the age of the lava. Fair enough, but in that case, they should all be the same, and they're not. Oh, and these three, they're all from the same rock too. Now, if you plot these on a graph and figure out the probability of those numbers actually being the same based on their differences in terms of the uncertainties that were quoted, you can see it's totally improbable that they could be considered the same age. So, based on the results that we get, it seems to me reasonable to conclude that none of these are particularly reliable. Now, there's another view of radiometric dating, which has been tried, and I call that radiogenic helium dating. And that's using a lead. Can you read that? That's really small, isn't it? Using the decay of uranium to lead in zircon. Now, zircon crystals are a crystal structure such when they form, lead doesn't fit, but uranium does. So when they form, they're pretty much always in the assumption that there's no lead in them, but lots of uranium. Now, when uranium decays, it emits 8 alpha particles. And alpha particles are actually helium nuclei. In addition, they emit electrons, and the alpha particles combine with the electrons and become helium atoms. Now, helium atoms are very small. Helium is a noble gas, so it doesn't form any compounds with anything. And it diffuses readily through just about everything. I mean, how many people have bought helium-filled balloons too long in advance of the party, right? So, this technique uses the zircon crystals obtained, or this experiment used zircon crystals obtained from a U.S. national laboratory that was drilling a very deep borehole in New Mexico. And these zircon crystals were sent to independent lab for analysis. And what they found was, what they measured were uranium-238, and the lead, and the helium, amount of helium in the crystals. What they found was an amount of uranium and amount of lead, and if you did that equation like you did the calculations in the manner we just previously described, they would indicate that the zircon crystal was about 1.5 billion years old. Now, in that length of time, one would expect that pretty much all of the helium that had formed would have diffused out of the zircon crystal. So you would have expected an amount of helium like this. What they actually found, like this. What they actually found was a huge amount of helium, up to 50% or more in some cases of the amount of helium that was produced by all of that uranium decay was still in the zircon crystal. So the scientists that did this experiment set about to calculate the rate at which helium would diffuse through zircon based on the amount that was still in the zircon and the assumption that the zircon was only about 6,000 years old. And you got a curve like this. It's a curve because the rate of diffusion depends on the temperature, and the temperature depends on the depth, and the zircon crystals came from different depths in the borehole. He did another calculation based on the assumption that the zircon crystals were actually 1.5 billion years old, and got this. Now you can see they both fit on the same graph, which makes you think that they're about the same, but they actually differ by a factor of 100,000. So they did that in the year 2000. In 2003, they were able to get some other zircon crystals from the same hole from the National Laboratory, and they sent those away to an independent lab to have the diffusion of helium through the zircon crystals measured. And here are the results. The measurements correspond almost exactly with the model based on the assumption that the zircon crystals were about 6,000 years old. In fact, when they did a recalculation for the best fit, they got an age of 5,681 plus or minus 2,000 years. So you can see again the difference between accuracy and repeatability or uncertainty. Uncertainty is pretty high, but the accuracy is pretty good. So what's the implication of this difference? Well, here is the assumption based in the old age measurement. You start out with some amount of uranium, 4.5 billion years ago, and it decays at this constant rate down to the present. At that time, you've got that much left, right? Now, if you back up 4,500 years, you would have that much left, and if you back up 6,000 years, you would have that much left. So now, suppose we had a different scenario. Suppose we had a scenario, it's just a recurse. There we are at the present with this much, and then those are the others, and then we go back up to the 1. Now, suppose you start 6,000 years ago with the same amount of uranium. You go for some period of time, maybe 1,500 years or so, at the standard decay rate that we know what it is today, and then you go through a period of extraordinarily accelerated decay, at the end of which you have the same ratio, the same amount of uranium left as if you'd waited 4.5 billion years. That means that from here on, the actual things that you measure, the ratio of uranium to lead, or lead to uranium, are no different between those two histories. So they cannot be used to distinguish between them. However, those measurements from the diffusivity of helium appear to be a measurement that does. Okay? All right, now let's go to the geological column. Here's a representation of the geological column. This geological column is generally considered to be all those layers of rock, but also it's all of the fossils that are contained within them. Now, one of the interpretive frameworks that is used for analyzing geological data is something called the law of superposition. It was formulated by a guy called Nicholas Steno, who is known today as the father of modern stratigraphy. And basically it says that when you have sedimentary rocks, which is what's in the geological column, if you have two layers of sedimentary rock, the one on the bottom was there first and the other one was put on top. You got that? Pretty profound, I thought. Now, if you look down the left-hand column, you'll see that there are times, durations associated with each one of those layers. 48 million years or whatever it is, and whoops. 48 million years and 66 million years. And if you apply Steno's law of superposition and just add all up, down here, the difference between the Precambrian and the Cambrian, you get about 600,000 years. And that's about where the fossil record starts. So the evolutionists interpret this progression of fossils up through the layers as being the succession of life. All right, well, we know from the Bible that the earth is only 6,000 years old, so where do we get all of these millions of years from? Well, mostly this guy. He was a lawyer and an amateur geologist, and he wrote a geology text in which he said, the history of our globe must be explained. Notice, this isn't something he extracted from the data. This is a presupposition he is imposing on the interpretation of the data. Must be explained by what? By what can be seen to be happening now. That is, he assumes that what we see in geological processes, sedimentation, erosion, earthquakes, volcanoes, whatever, have always gone on exactly the same as we see them today, at the same rate throughout history. So it's called uniformitarianism. Everything's happened uniformly. Then he goes on and says, no powers are to be employed that are not natural to the globe. There you are. There's that naturalism thing showing up again. It's naturalistic uniformitarianism. Now notice what he's done right off the bat. By his presupposition, he has precluded explaining the geological features using a global flood. Because we don't see global floods today, and it wasn't a natural event. It was a supernatural event. So no matter how well it might explain the evidence, you're not allowed to use it. You're in this box, right? How does it work? Well, here's the evidence. If you're going to use uniformitarianism and naturalism, you measure the thickness of a rock, you divide it by today's rate of sedimentation, and you find out how long it must have taken to define that rock. Or the same thing for erosion. And the math is pretty simple, right? However, consider this. I know it's coming. This is coming. Suppose you get up one morning and you look out in the ground, and there's a meter of snow on the ground. And the snow is falling at the rate of 1 millimeter per hour. Okay? You say, well, weather processes have always gone on the same as they are today. You do the calculation and you find out, it took 6 weeks to accumulate that snow. But you have a written record from the preceding evening that tells you there was no snow on the ground and none was falling. So that's obviously wrong. You can change time for intensity. And Mount St. Helens indicated that applies to geology. Here's a geological feature that didn't exist before Mount St. Helens erupted. A wall of rock. You can see how big it is. There's actually 3 different kinds of rock here. One on the bottom is from the ash cloud. The one on the top is from a mud flow. But the one in the middle is really interesting because it's made up of many, many fine layers. Uniformitarian paradigm says that all that happens slowly over a long period of time at the rate of 1 or 2 layers per year in still water. So if you want to know how long it took to lay down that rock, you just count up the layers. However, in reality, that whole thing happened very quickly. Be there in a minute. There we go. Happened very quickly when something called a pyroclastic flow, which is just a big ball of gas full of sediment, went roaring past here horizontally and left us behind. The whole thing took only 3 hours. So it doesn't take a long time. And in fact, remember Steno? University of Berkeley has an entry in its website that says it should be remembered that Steno's law, superposition, is a statement of relative time, not absolute time. 2 rock layers, in principle, could have formed millions of years apart or a few hours or days apart. Steno himself saw no difficulty in attributing the formation of most rocks to the flood mentioned in the Bible. It then goes on to talk about fossils. It says that he noticed that of the 2 major rock types in the mountains near Flores, the lower layers had no fossil, while the upper ones were rich in fossils. He suggested that the upper layers had formed in the flood after the creation of life, while the lower ones had formed before life had existed. So both the geological column and the fossil record are compatible, just consistent with what you would expect reading the first 11 chapters of Genesis as actual history. Now, if you're interested in further exploring this, I'd like to highlight some resources, some of which you can find on the table at the back. For answering questions, which is the theme of this conference, good book would be this one, because it has the answers to the 60 most frequently asked questions that CMI speakers have encountered. This is another excellent book. It deals with evolution in particular, although it also has chapters on the geological record and radiometric dating and cosmology, which we'll talk about later, and it also has a DVD. Specifically with respect to this topic, these are excellent resources, some of which are here. The first one isn't here. The other 3 are back at the table. Now, I'd also at this point like to highlight another resource that we consider to be our number 1 tool for getting information into your hands. It's a magazine called Creation Magazine that is published 4 times a year. We'll have examples back there. Some of you may have already thumbed through it. It's a very high-quality magazine, 56 pages in full color on good paper. The articles are all scientifically oriented, up to date on terms of the discoveries, written by scientists, so they're technically correct, but not for scientists, so they're easy to read. They range in size like a couple of paragraphs to a couple of pages. The subscription for this is really easy. It costs $7.50, and it's billed to either your checking account or a credit card every 3 months. And for that, you get a hard copy, a digital copy, which you can download simultaneously onto up to 5 devices. If you sign up at this conference, you'll get the first issue to take back free and also a free DVD. So I'm going to ask the folks with the clipboards if they'll now send them around again. Now they should have a form on them that looks like this. If you'd like to subscribe to the magazine, take one of these forms. There are 2 or 3 on a page, tear it off, and fill in on this side the information where it needs to go. So the address, or the person's name, the address, the phone number, and the email address, and that's important. Now, if you're going to get this subscription for yourself, that'll be your information. You can also give this as a gift, in which case that's the information for the recipient, and your information needs to go over here. Then it's really important that you fill in the back. On the back, you'll find a place for your signature and the date. which is the information we need in order to, or the authorization we need in order to bill your credit card or your bank account. And then we need the information about either the credit card or the bank account. And once you get that all filled in, or when we have a break, if you bring it back to me at the table, you can pick up your free gifts. All right, now let's switch over to evolution. And here we need to be aware of this same vocabulary, different dictionary again, because people often use the fallacy of equivocation when they're talking about evolution. They'll start out defining evolution to be change over time. Then at some point in the conversation, they'll change that to be change over time plus descent from some common ancestor way back when. And they'll just keep on referring to it as evolution. And then they'll change to mean not only that, but the origin of life by naturalistic means. So they'll say, well, since we see change over time, and we'll all agree with that, then that means we all descended from a common ancestor. And because there was a time when there was no life and now there's life, well, that means life must have happened by accident. None of that follows from the initial observation. So let's look at that in a little bit more detail. From the naturalistic perspective, we have this process called abiogenesis, in which highly energetic chemistry, as they refer to it, is said to have produced the first simple self-replicating organism. Then over the next approximately 500 million years, that simple organism transformed into something substantially more complicated called the last universal common ancestor, which is the ancestor from which all life forms on Earth subsequently evolved. And that happened over the next 3.8 billion years as a result of mutations and natural selection. Over on the creation account, or creation side, as described in the Bible, we have the initial event of creation, which happened over 6 days and resulted in several created kinds, a pair of each of a number of created kinds. Now, we don't know exactly what those kinds were, but those are not unreasonable, maybe, suggestions. A cat kind, a dog kind, a horse kind. We do know there was a mankind, and the first two of those were Adam and Eve. Then, of course, we had the fall. And after the fall, we had, as a result of mutations in natural selection, transformation into today's species. And then, of course, round about that time, there was a global flood. Now, these two start with the same state, no life, and end with the same state, today's species, but there's a different history explaining how you get from one place to the other. Oh, yes, okay, sorry. But there are some implications that make the two different. In the one case, life starts extremely simple and gets increasingly complex. In addition, it requires the creation of huge amounts of new genetic information. All right? On the other side, life starts complex, we're all made perfect and genetically perfect, and after the fall, the genetic information starts to degrade and be reduced. Those are two quite different things that might show up differently in what we can actually see happening. Not only that, according to the Bible, we're all descended from one pair, right? And we spread out from the Middle East after Babel. Oh, well, we're all descended from the same pair. Oh, subject to the population bottleneck that happened on the ark. Now, people who've studied chemistry or biochemistry probably have heard about the Miller-Urey experiment, which was purported to show how life could have started by naturalistic means. What they were able to do was create a number of amino acids by this technique, and amino acids are the building blocks of proteins, and proteins are the building blocks of life, so they said, we've demonstrated how life could have started by accident. But in actual fact, that doesn't stand up to scrutiny. Just connecting the amino acids together into long chains to form proteins is prohibitive. This gentleman, who was an evolutionist, wrote a book in which he said, the origin of life by chance in a primal soup is impossible, in probability in the same way that a perpetual machine is impossible. The extremely small probabilities calculated in this chapter are not discouraging to true believers. However, a practical person must conclude that life didn't happen by chance. The belief that life on Earth arose spontaneously from non-living matter is simply a matter of faith in strict reductionism and is based entirely on ideology. Although at the beginning, the paradigm was worth consideration, now the entire effort in the primal soup paradigm is self-deception based on the ideology of its champions. He wasn't pulling any punches, was he? In any event, stringing amino acids together into proteins isn't really the crux of the issue, as we now know it. This fellow, also an evolutionist, pointed out that while we can make amino acids naturalistically, transforming those into proteins just by adding energy doesn't actually work. In any event, we now know that the secret of life lies not with the chemical ingredients, but with the logical structure and organizational arrangement of the molecule. Biological information, that's the stuff in our DNA, is not encoded in the laws of physics and chemistry, and it cannot come into existence spontaneously. There is no known law of physics able to create information from nothing. All right, we go back to this picture. This has some real implications, right? We put these quotes on here. What does that mean? Well, it means that's not possible, nor is that. However, this is, and so is that. All right, the other thing we hear is that mutations in natural selection produce all this cool new genetic information that we need. Well, let's have a look at that. What is a mutation? Well, a mutation is a change of the existing nucleotide sequence of a genome of an organism. Mutations result from unrepaired damage to existing DNA or to existing RNA genomes, errors in the process of replication of existing DNA, or from the insertion or deletion of existing segments of existing DNA. Well, don't create any new information at all. They just mess up what we already have. Mutations also may or may not produce any discernible changes in the observable characteristics of an organism. So, they don't create any new genetic information. They just make a mess of what we already have. What are the impact? Well, they reduce the fitness of the organism. That is, its ability to survive. Remember, evolution is survival of the fittest, right? So mutations keep making things less fit. One of the earliest theories was done by this Japanese guy, and he suggested that most novel mutations are highly deleterious. That means really bad, with a small fraction being neutral. Another guy had an alternative theory in which he said they were really kind of two sets. But both of those theories have the majority of the mutations being very bad and only a few being good. And that's supported by real science, repeatable experiments. Here's an example of a distribution of fitness effect. So across the bottom we have fitness from 1 to 0. 0 is you're dead. 1 is you're good. These are the neutral mutations, the ones that don't change the fitness. All the rest of these are bad. These ones are so bad, the organism died. Over here we have the advantageous ones, and as you can see, they're very small. Now, if we model this with this, I could use that to calculate the effect generation over generation of a population of organisms. So you start with everybody fit. You have the next generation. You just pick a number from this table based on the probability of it occurring and multiply it times the start, and you get something that looks like this. All right, for 10 individuals over 13 generations. Notice what happens. The fitness goes to 0 eventually. That's because you keep multiplying by a number less than 1. And eventually, and some of them are lethal, so eventually it all goes to 0. Now, remember it said mutations may or may not produce an observable change. Well, this is Kamuro's distribution of the fitness effect. So you can see the frequency of occurrence is up the left-hand side, and the effect on fitness is on the bottom. So most of the mutations are negative. And there's this region in here which he referred to as the no selection zone. That's where the organism doesn't change at all, so natural selection doesn't know what happens. And all of these are the only ones that it can select for. And they're all negative. Right? Now, he said there were no beneficial mutations. Dr. John Sanford, who wrote the book Genetic Entropy, of which I have a copy or two out there, said, well, there are probably a few. Right? So if you use Dr. Sanford's distribution, you get, and repeat the experiment I did before, you get this. So it's not quite so dramatic, it takes a little bit longer, but eventually everything goes to zero. Now, Dr. Sanford has developed a very sophisticated program that actually models mutations in natural selection as they actually happen and gives you control over a lot of parameters like the population size and the selection pressure and blah, 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 blah. He finds exactly the same thing. The effect of mutations is to drive species to extinction. Well, what about natural selection? Now, I'm going to illustrate the effect of natural selection using dog hair length as an illustration. And while this is simplified, it's still technically correct. And let's assume that the length of a dog hair is encoded in the genes in terms of a short hair gene and a long hair gene. And if you have one of each, remember we each have 2 copies of each gene. So if you have a long-haired and a short-haired, you have medium-length hair. Now, if these dogs have puppies, they can pass that information on in a number of ways. They can each pass on, both mom and dad can pass on the short-haired gene, in which case you get a short-haired dog. Mom can pass on one gene, dad can pass on the other, or vice versa, in which case you have a medium-length hair dog. Or both mom and dad can pass on their long-haired gene. So you get a dog with long hair. Now, somebody might say, well, look, now we got different hair lengths, so we've got new genetic information, but that's not the case. There is no new genetic information. It's just a different combination of what we already had. All right, now what happens with natural selection? Well, if all these dogs get to go somewhere really cold, like Sault Ste. Marie, then these dogs might die because it's so cold. So might these. So now we're left with only the long-haired dogs. If they have puppies, they can only pass on the long-haired gene. So all their puppies will have long hair. So natural selection has now eliminated the short-haired gene from the population. So it is removing genetic information, not adding genetic information. Now, another thing is, if now these dogs, we have a severe case of global warming, and it's really hot in Sault Ste. Marie, these dogs are all going to die. So they're all going to go extinct. So once again, now mutations in natural selection act to drive things to extinction. So mutations are always making our genome worse. And we get about 100 to 300 new generations per person or new mutations per person per generation. Geneticists have estimated variously that represents a decrease in our fitness from 1% to 2% per generation. Some even have gone as high as 5%. Natural selection can't stop that. Can only slow it down by getting rid of the worst cases. So what does that tell us on here? Well, it tells us that that's not possible and that's not possible. That's not what we see in the genetics research. This is what we see. Right? We started perfect and we're getting worse. And that's what the evidence says. Now I want to talk about 2 other kinds of DNA, mitochondrial DNA and the Y chromosome DNA. Mitochondrial DNA is the DNA in the mitochondria, surprise, in our cells. And it has the characteristics that it's only passed on from mothers to their offspring. So that means if we have a lady with yellow mitochondrial DNA and she keeps having females in her lineage, her DNA will stay in the population. The lady with the green mitochondrial DNA, eventually her line has only male offspring, and that's the end of her mitochondrial DNA. Scientists have studied mitochondrial DNA from people all around the world, come to the conclusion that all modern humans came from one female. Y chromosome DNA is the stuff that makes men men, right? And so it's passed down from fathers to sons. And if fathers have daughters, their Y chromosome DNA has gone out of the population, just like the other side. Scientists have studied Y chromosome DNA from people around the world, well, men around the world, come to the conclusion that all modern people have come from one man. They call these 2 people mitochondrial Eve and Y chromosomal Adam, believe it or not. Using the mitochondrial DNA, they have charted out that people spread around the world from somewhere in North Africa or the Middle East. And you'll know that's over here. And you'll notice they've got L1, L2, L3. That means that they have been able to identify 3 distinct lines of mitochondrial DNA. What does that sound like? 3 daughter-in-laws of Noah, right? And the population bottleneck of the flood. Now, using something called a molecular clock, they've attached some timelines to this, which shows it starting about 130,000 years ago. Now, population geneticists usually use 30 years as representative of a generation. So that means that was like 4,000 plus generations ago. But if our fitness has been decreasing at 1% per generation, it is currently at 10 to the minus 19. Now, those of you who are familiar with exponential notation, that's effectively 0. We would have gone extinct a very long time ago, but obviously we didn't, because I'm here talking to you. Now, in the biblical picture, this migration started after Babel, so it was less than 4,500 years ago. A lot fewer generations. In fact, using the Bible, we can count up that from 6,000 years ago, there have been about 155 generations. So that 1% decrease in fitness per generation currently puts us at 21%. Not great, but still apparently adequate, because we are here talking to each other. Now, here we are again. Guess what? What we see in the genetics research is exactly what the Bible says we should see. Neither of those are actually predictable from the evolutionary account. They are potentially explainable with those unsubstantiated just so stories that Dr. Lewinton talked about. Now, if you want some more resources on this, those ones are still good. And then we have these three that pertain directly to this. Okay, now I have a decision that I need your help with. I've run out of time. I haven't talked about the Big Bang. Should I stop and allow some time for questions, or would you like me to finish the Big Bang? Well, that was an either or, so you can't answer yes. Go ahead. Okay, talk about the Big Bang. This is the secular view of the Big Bang. Sometime there was nothing, then there was a quantum fluctuation, and there was everything. Somehow all of that mass and energy that we can currently see in the universe got transferred out of something called the quantum vacuum, into real space and time. Shortly after that, very shortly after that, as you will find out, there was this period of inflation over a very short period of time in which the universe expanded by an unimaginable amount, but it was still a very hot, dense plasma, so that no light was actually escaping from it. That didn't happen until some 400,000 years later, when this afterglow light was able to come out, and that's what people refer to as the cosmic microwave background radiation. We don't have any stars yet, so we have what they call the dark ages, with the first stars forming about 400 million years ago after large clouds of helium gas had condensed and started burning, or nuclear fusion. Now that we got stars, we can develop some galaxies and planets and stuff like that. We have this Big Bang expansion going on for 13.7 billion years. And lately they've been saying it's expanding faster because we got some dark energy somewhere. All right, now in all of this, the sun appears about here, and the Earth a little while after that, and the moon a little while after that. And then there's this issue of the distant starlight dilemma that I referred to. Here's a star that formed way back there, and here's the Earth way out here at the far end now. And if this was 10 billion years away, 10 billion years ago, how is it that we can see that light if the Earth is only 6,000 years old? All right, let's look at a couple of these things at the origin. There are problems, incidentally, with every aspect of the Big Bang, things where it really doesn't fit the physics. But I'm just going to look at two. The quantum fluctuation, where, remember, kind of nothing creates everything. But this guy says, he's a PhD in astronomy. There was a very real problem in explaining how it all got started in the first place. You cannot fudge this by appealing to quantum mechanics. Either there is nothing to begin with, in which case there is no quantum vacuum, no pre-geometric dust, no time in which anything can happen, no physical laws that can affect change from nothingness into somethingness, or there is something, in which case that needs explaining, right? So this quantum fluctuation doesn't actually explain anything. It's just more of a problem. Then this issue of inflation, as I said, it was very short, made a huge change in size. They have no idea what caused it to happen. No idea what propelled it. It had to be some kind of anti-gravity force to spread all of that matter around. And they have no idea why it stopped. Not only that, there's no empirical evidence for it, and you can never do an experiment to test it. You can't even see it, because it all happened before we could see anything, which is the 400,000 years when the afterglow became visible. And it was actually introduced simply in order to solve a bunch of problems between what we observe and what was predicted. And a short while ago, a couple of years ago, 4 years ago already, they had a conference that was 50 years after the discovery of the microwave background radiation, when this gentleman, big name in the field, made the statement that inflation isn't falsifiable. Well, we all knew that. It's falsified, he said. There's so much evidence now that suggests it's wrong. So many problems with the Big Bang that a group of scientists wrote an open letter to the scientific community, published in a very prestigious journal, the New Scientist, in which they said the Big Bang, this is just some of the letter, the Big Bang relies on a growing number of hypothetical entities, things that we have never observed. Inflation, dark matter, and dark energy are the most prominent examples. But the Big Bang can't survive without these fudge factors. Everybody in high school knows what a fudge factor is, right? It's a thing you need in order to make your experimental results work. Same with the professionals, I guess. What is more, the Big Bang Theory can boast of no quantitative predictions that have subsequently been validated by observation. Well, hang on. I thought that's what science was all about. Now, that was in 2004, so maybe some things have changed. Well, as recently as 2013, there was a seminar in Australia in which the abstract of which read, in part, it is found that each test which has been designed shows that the Big Bang to fail, such that the Big Bang model needs to be discarded. Now, let's adapt this diagram to the biblical account. So instead of a quantum fluctuation, we have God speaking. Right? He creates water on day 1, it expands on day 2 by separating the waters below from the waters above, the earth on day 3, the sun, the moon, and the stars on day 4. Then there are parts of the Bible that talk about God stretching out the heavens, right? And one of the biblical cosmologists has a model in which he talks about God stretching out the heavens. He takes into account God stretching out the heavens after the sun, the moon, and the stars have been created on day 4. So let's assume that happens in there. Now what we have the waters above stretched way out to the extreme edge of the universe. So this afterglow light pattern, this cosmic microwave background radiation, could very well be radiation from these waters above. There aren't any dark ages, because we already got everything made, because the first stars were made on day 4. We don't have to wait for galaxies and all that kind of stuff. We don't have 6,000 years of, 13.7 billion years of expansion, only 6,000. And this acceleration doesn't actually exist either. Oops, what did I do? I just hit the wrong side of the pad again. Sorry. Now, you can chart this change in size as a function of time on a graph for the Big Bang. So it starts out infinitesimally small, immediately goes through a period of inflation, at the end of which we get the CMB, cosmic microwave background radiation, being the afterglow of the initial Big Bang. And then we have 13.8 billion years of expansion. On the other hand, we could have a diagram of what I call the Big Bible, which starts small, exists, and that's, according to Dr. Hartnett's model, exists in a relatively small state for about 4 days. And then God stretches out the heavens, and we have the cosmic microwave background radiation being the radiation from the waters above. And then we have 6,000 years of expansion. Now, these kind of look very similar. So one might say, well, maybe the Big Bang is what God used to make the universe. But if you look in detail, the sequence of events, you'll find it doesn't fit. He made, in the Big Bang, stars happen first, then galaxies, the sun away out here, then the earth, and then the moon. In the Bible, it's the earth first, then the sun, then the moon, and then the stars. And those all happen in the first 4 days, not spread over 13.6 billion years. So, but then as we've seen from the previous slides, this contravenes the laws of physics, and this does as well. So you can see what I meant when I said way ahead that they assume the universality of the laws of physics, except when they don't, and need their own miracles. So I think it's safe to say that the Big Bang doesn't really, the evidence really isn't consistent with the Big Bang. All right, so how do we see those distant stars? Well, there are actually several explanations for that within a biblical cosmology. The first one that I'm aware of, well, not the first one, but the first reasonable one was white hole cosmology. It was put forward by a Dr. Russell Humphreys. And it uses gravitational time dilation. That is, that clocks run at different rates depending on the gravitational environment in which they find them. And by incorporating that into the model, he can account for how we can do that. There was another one, the New Physics Cosmology by Dr. John Hartnett. It was based on a secular scientist's new model of the universe and results in an acceleration-induced time dilation. That is, when God stretched out the heaven, things get accelerated, and that makes clocks run at different rates at different places. Dr. Humphreys has recently proposed another one called what I call the timeless zone cosmology, which starts with Einstein's equations and again uses a gravitational time dilation to account for the time lapse. There's a more recent one been suggested by Dr. Jason Lisle, which is also based on Einstein's equations. And since we can only ever measure the two-way speed of light, there's some flexibility in how you define the speed of light in one direction. And this model assumes that the one-way speed of light towards the observer is always infinite. And then the other one was half c. And then there's a final one, most recently, called what I call creation time coordinates. And that's the one I'd like to talk about briefly, because it's kind of cool. To do that, we need a little bit of background on special relativity, where they deal with diagrams like this. So here we have an observer, and here we have a spatial dimension, x, and then in this dimension we have a time dimension, but it's been transformed into a spatial dimension by multiplying the time by the speed of light. These two things are events. This is a particle world line. It's the path that the particle takes through time and space. And this is the particular world line for a light particle. And that then gets us to this idea of light cones. There are future light cones. That would be, in this diagram, this. That's the part of space-time that will see an event that happens at the location E at time 0. Okay, so then we have past light cones. That's the other end. So that's the volume of space-time that can be seen by E at time 0. All right, now using these, we can create this diagram, which is the light cones, combined light cones for day 4 and day 5. So here's the Earth. And so that's the Earth on the start of day 4, and that's his past and future light cone. So anything above that is space-time that will see something that happened on Earth in day 4. Anything behind that is something that inside the cone is something that the Earth can see on the start of day 4. Then we can do the same thing for day 5. So the space between these two is day 4 on Earth. This would represent we called it the hypersurface of where if stars were created in that location of space-time, they would be visible to Earth on day 4, or between the start of day 4 and the start of day 5. So what this model does is assume a particular time system, time coordinates, for measuring time. And it's measured relative to the Earth and how things happen on the Earth. So day 0 is the day that the Earth is created, and day 4 is the day during which all of the sun, the moon, and the stars were created in this time coordinate system. It's kind of like we could all adopt Greenwich Mean Time. Be a bit strange, but that would mean that events would happen at the same clock time, but, if you like, different times in relationship to the sun. Right? But that's a perfectly legitimate time system. In fact, some people have advocated for that. Now, more resources. Those are the equally applicable. The Big Bang is an excellent book for talking about all the problems with the Big Bang, and then the others are specifically with respect to this topic. We've heard a lot about this. This is the theme text for the conference, but we must never forget to include the last part of that. There's another one which encourages us to be able to demolish arguments. To do either of these, of course, we need to have the information to do it. And while you're going to get dumped on with a lot of information at this conference, we all know what will happen when you walk out, right? Start forgetting it. But if you are able to review things, you will forget less of it and remember more of it, which is why it's so important to have resources. There are a couple of other excellent ones out there that cover the whole waterfront. The Genesis Account and the Genesis Academy, depends on whether you like to read or watch videos, and I encourage you all to sign up for that. In closing then, hasn't science disproved Christianity? No, it hasn't.